So let us look at a question from classical mechanics that was asked in CSIR NET December 2018 paper. It says the motion of a particle in one dimension is described by the Lagrangian L is equal to half into dx dt the whole square minus x square in some suitable units. And it asks us to calculate the value of the action along the classical path from x equal to 0 at t equal to 0 to x equals to x naught at t equals to t naught. Okay, so we have to calculate the value of the action for the Lagrangian given. For that, we need to know how an action is defined in classical mechanics. And action is defined as integral of L dt from some initial time to a final time. For the given Lagrangian, we have S is equals to integral of half into dx dt the whole square minus x square dt from 0 to t naught. Okay, if you write dx dt as x dot, it becomes half into x dot square minus x square dt from 0 to t naught. Now if we do integration by parts in the first term, which is x dot square, we get the action as half into x dot x from 0 to t naught minus integral of x double dot x dt from 0 to t naught minus x square dt from 0 to t naught. Now to simplify this expression, we need what is x dot and what is x double dot, and for that we need to use the condition given in the question that we are asked to evaluate the action along the classical path. Now, what is a classical path? A classical path is the path taken by a system to evolve from a certain initial configuration to a final configuration if the evolution is governed by the laws of classical mechanics. That means that the path that the system takes to evolve from an initial configuration to a final configuration is decided by the laws of classical mechanics, and such a path is called therefore the classical path. And a classical path is given in classical mechanics by the Euler-Lagrange equation, which means that any path which qualifies to be called a classical path has to follow the Euler-Lagrange equation. Now for the Lagrangian given in the question, the Euler-Lagrange equation, which is d dt of del L del x dot equals to del L del x, becomes x double dot is equals to minus x. Now this is a simple equation. Right? There's a simple equation to solve, and the solution comes out to be x of t is equals to a sin t plus b cos t. Now to calculate the value of a and b, we use the initial conditions, and we find that x of t, which is the trajectory of the particle, you can say, looks like x naught into sine t by sine t naught. Now if we differentiate this expression, we get x dot as a function of t, which is x naught into cos t by sine t naught. And when we replace these two, which is x dot and x double dot, x dot is double dot is calculated here, x double dot is equals to minus x, and x dot is equals to x naught into cos t by sine t naught. If we replace these two in the equation that we got for the action, we finally get the action calculated as half into x dot at t naught into x at t naught plus x square dt from 0 to t naught minus x square dt from 0 to t naught. So finally the action comes out to be half into x naught square cot of t naught. Okay, so this is the action for the Lagrangian given in the question, calculated for the classical path that the system follows from x equals to 0 at t equals to 0 to x is equals to x naught at t is equals to t naught. Okay, therefore the correct option to this question has to be option 3, half x naught square cot t naught. Okay, so thank you for watching the video, and if you like the video and if you're liking the videos that I've been uploading, please like, comment and subscribe the channel. Thank you.